So we were talking about laws of probability, and we saw this picture before where we have a set of exhaustive and mutually exclusive sets here called the H's. We used this picture before when we discussed the law of de-anding, but now we're going to use the same picture to talk about what maybe is the greatest little probability theorem of them all, so-called Bayes' theorem. This theorem is named after Thomas Bayes, an English minister who lived in the English countryside in the 18th century. He corresponded with Sir Isaac Newton on a number of points, and he's remembered today primarily for this one little theorem, which we can prove in a couple of lines. So the theorem starts off as this. Suppose that we want to know not the probability of B, which is what we previously were looking at, but the probability that we're in one of these sets H sub I, where in the picture above I goes from 1 to 5, given that we're in set B here. So by the definition of conditional probabilities, we can write that as the probability suppose we're dealing with H2. The probability of H2 and B, that's this little segment here, divided by the probability of B, which is this segment here. And that would be the probability of being in H2 given that we're in B. Now, basically we get to apply our two laws from the previous segment. The law of anding to the numerator, so the probability of HI and B, but now we do it this way around. It's the probability of B given HI times the probability of HI. And then in the denominator, let's apply the law of de-anding and break that probability up into its pieces in the different H's. So that's the sum over J, the probability of B given Hj times the probability of Hj. You might want to stop the video and see that you understand how by using anding and de-anding I can get the original desired expression into this form. Notice the denominator here is simply the sum of exactly the same expression in the numerator, but over all possible values of the subscript here called j. Therefore, we often write Bayes' theorem as a proportion sign. We just write the probability of hi given b is proportional to its numerator, because all the different hi's, I equals 1, 2, 3, 4, 5, will have the same denominator. And we could recover that denominator by just knowing the right-hand sides by essentially just adding them up and dividing the numerators by that result, which is to just restate the obvious from the theorem here. And so this is the form that one usually calls Bayes' theorem. Notice that this gives a way of reversing the order of a conditional. In other words, if we can compute the probability of B given H sub I, then this tells us how to compute the probability of H sub I given B, with just the additional caveats that we have to know the probability of the H sub I unconditioned here, and that to get an actual probability we'll have to resolve this proportion sign by computing. This is called the Bayes denominator. As a theorem of probabilities, there's nothing that one can object to in Bayes' theorem. It simply is a theorem. It follows from the axioms of probability. The controversy between the Bayesians and the Frequentists arises when we give an interpretation to the H's as hypotheses. And we're going to use Bayes' theorem to compute what is the probability of a hypothesis given some data. Now, think about that, the probability of a hypothesis. What if my hypothesis is that it rained yesterday. Um, Frequentists would say it's not meaningful to give a probability to whether it rained yesterday because it's already either happened or not happened. In some sense, the probability of that hypothesis is either 0 or 1. We just don't know which it is. However, from Bayes on, Bayesians, like us, I think by now you ought to consider yourself a Bayesian, have learned that it's a fantastically powerful and useful thing to be able to assign probabilities to hypotheses. And as I think I mentioned in the previous segment, in real life, the war between the Bayesians and the frequentists has been over for a long time, and most statisticians, including us in this course, adopt a mixture of techniques appropriate to the problem at hand. A nice paper that reviews the history of this so-called war is one by Efron, and that's on the course website. Notice that to use Bayes' theorem, you have to have those H sub i's. You have to have a complete set of EME hypotheses to work with. And that's perhaps the principal weakness of Bayes' theorem, that you can meet problems in which it's not so easy to write down an exhaustive and mutually exclusive set of hypotheses. Sometimes your hypothesis is, well, I wonder if H sub 1 is true, and if it's not H sub 1, well, I don't know then what it is. And in that kind of situation, you're not going to be able to be a Bayesian, or at least not a very powerful Bayesian. We'll see examples of that later in the course. Well, this might seem a little abstract, but let's work a couple of examples using Bayes' law. These are examples so close to simply being probabilistic that I don't think frequentists would argue with them, but they give the idea of what we're then going to do in a more complicated way. So here's the story of trolls under the bridge. It turns out that there are bridges, and there are trolls, and they're bad. There's a picture of one. And there are gnomes. Here's a picture of another one. And the gnomes are at least benign. I don't know if they're good or not, but they're benign. Now, the rule is that every bridge has exactly 5 creatures under it. And if we look at all the bridges in the land, we see that 20% of the bridges have 2 trolls and 3 gnomes. Another 20% of the bridges have 1 troll and 4 gnomes. We're going to call this hypothesis 1 when we come to any particular bridge, and we're going to call the second one hypothesis 2. Hypothesis 3 is the remaining bridges, 60% of them, and those have no trolls. Those are completely benign with 5 gnomes underneath the bridge. Okay, if you got the setup, because the problem is now as follows. Before crossing a bridge, a knight captures one of the 5 creatures under the bridge at random. It is a troll. And the knight now reasons as follows. I have an 80% chance of crossing this bridge safely. Because, he says, I know I'm not in this 60% case, because otherwise I couldn't have caught a troll. And in this case, which happens in 20% of bridges, there is just 1 troll, and I just caught him. So I only have to worry about this case, the 20% case where there were originally 2 trolls under the bridge. And therefore, we get the knight's conclusion that he has an 80% chance of crossing safely. In other words, that the bridge satisfies hypothesis 1. Is this right? How could it be wrong? He's eliminated one way or another these cases, and the remaining case is only 20%. No, it's completely wrong. Stop the video and think about it until you see that this just can't be what the right answer is. Now let's work it out. Here's the outcome space, and for convenience I've divided it into 5 columns, each supposed to be containing exactly 1/5 of the probability, and that's just so that I can keep track more easily of these probabilities. So hypothesis 1, which occurs 1/5 of the time, has 2 trolls, the pink squares. Hypothesis 2, another fifth of the time, has 1 troll, and hypothesis 3 is all 3 of these columns, adding up to 60%, and has no trolls in them. Okay, let's use the letter T to mean the night captures a troll. So what we're interested in is the probability of each hypothesis, 1, 2, and 3, given that the knight has captured a troll. Now we simply use Bayes' theorem. That's proportional to the probability of these two arguments the other way around, the probability that he captures a troll given that he's in each of these hypotheses, times the probability of that hypothesis. So now we just turn the crank. The probability of H1, that's the interesting one because that's the unsafe one for the knight. The probability of H1, given that he captures a troll, is the probability that he captures a troll given that we're in H1. So that you look up this column and you see that that's 2/5, and I've written 2/5 right here, times the probability of the initial probability, the unconditioned probability of being in hypothesis 1, and that's the width of this column, and so I've written the 1/5 right here. So that's the Bayes numerator. The Bayes denominator is exactly the same formula, but I now have to write 3 terms in a sum for all 3 hypotheses hi. So the first one is exactly the same as the numerator that we just computed. The second one, I'll do it from right to left, the 1/5 is because that hypothesis occurs 1/5 of the time, and this 1/5 is because 1/5 of the time given that hypothesis, the knight captures a troll rather than one of the 4 gnomes. And then the third term in the sum is the 3/5 remaining. That's this P of H3, that is to say these 3 columns. But it's times 0 because there's no probability at all of him capturing a troll under these hypotheses. So what is the answer? The numerator is 2/25, and the denominator is 2 plus 1 is 3/25, and so the answer is 2/3. That is to say, there's a 2/3 probability that we are under hypothesis H1. So his chance of crossing safely is only 1/3, 33 1/3%. He thought it was 80%. And before he even captured a troll, before he, as we'll say, saw the data, he had a 60% chance of crossing safely because he was in one of these 3 things. So it's a little bit paradoxical. Capturing a troll actually made things worse for him. It decreased his chances of crossing the bridge safely from 60% to only 33%. And by the way, 80% was never the right answer. There's no reasonable question you can ask in this problem for which the answer is 80%. Now, I'm over-dramatizing this perhaps a little bit when I say that by capturing a troll, he made things worse. If you think about this for a minute, it was actually the fact that he saw a troll that made things worse. Because by seeing a troll, he acquired some data. He acquired the data that he must be in these 2 columns and not in these 3 columns. Capturing the troll actually made things a little bit better because in the case of this column it eliminated the threat, whereas in the case of this column it eliminated only half of the threat. However, it is true in this problem that the knight now has only a 1/3 chance of crossing safely. So what conclusions can we draw from this? Here's the main lesson that we've learned. Data changes probabilities. There was a probability of him crossing safely before he saw the data, and that was 60%. And there's a probability of him crossing safely after he saw the data, and that is 33.3%. Probabilities after assimilating data, or as we would say in probability notation, probabilities given the data, are called posterior probabilities. And the power of Bayes' theorem is that it gives us a mechanical way of computing posterior probabilities over a wide range of problems. Now, we've said before that to Bayesians, Bayes is a complete calculus of inference, that it should tell us everything that we need to know. And so it would be useful to check that this all works out in the sense that R.T. Cox put forth as one of his desirable propositions about any calculus of inference, that if we see two sets of data, D1 and D2, we should get the same answer independent of the order that we see them in. Now, if you look at the picture of what we mean by that, the H's are now the hypotheses, and when we see data 1, it maybe restricts us to this set of outcomes. And then when we see data 2, it restricts us to this set. And it's obvious that the overlap, the intersection set here that's been colored green, is independent of the order in which I write down D1 and D2. So we know this probably has to work out. But it's instructive to see how, by actually just doing the math, it does work out. So we start off with a probability of a hypothesis before we see any data. That's called a prior probability. That's a term we're going to be using a lot. Okay? And we multiply it by the probability of the data given the hypothesis, and that gives us one of the numerator terms in Bayes' law, and therefore it gives us that the probability of that hypothesis given the data is proportional to that. Now suppose we see D2. Here's the key point. The prior probability going in here was P of H1, but the posterior probability coming out is, P of HI, is P of HI given D1. And this posterior probability becomes the prior probability of the next stage of the calculation. Okay? So we want to get the probability of H sub I given both D1 and D2. We now apply Bayes' law to this, but the D1, which we've already seen, just stays passively on the right-hand side. So Bayes' law says we can reverse the HI and the D2, here and here, here and here, and we just keep the D1 going along for the ride, because we've already renormalized the outcome space, in a sense, to just be living within D1. Okay? And so similarly, the prior probability here also has a D1 that's just going along for the ride, and this is the term that we got from the previous calculation up here. Now, let's in fact use this expansion that we got on the first step and expand this second factor into these two factors. Okay. And now, regrouping and staring at the first and second factor here, you'll see that HI is just passively going along for the ride on the right-hand side of both of those. And then what we have here is one of those laws of conditional probability. The probability of D2 given D1 times the probability of D1. Okay? Well, that's the probability of D1 and D2, with, again, the H sub I being the given in here, here, and here. So that's the answer for those two terms. We have this term right here. And you can see that we've gotten the desired answer. How can I see that? Because I've gotten that the probability of the hypothesis given both sets of data is the probability of both sets of data given the hypothesis times the prior on the hypothesis, and this being a logical AND operation, we would get the same answer either direction, D1 first or D2 first. That's essentially just the same argument that we did up here, drawing the pictures that the overlap is independent of the order in which they're put down. So to a Bayesian, all priors P of H sub I are actually priors P of H sub I given some data. That data might be the data that you're explicitly given in the problem, or that data might simply be background information that you know about the hypotheses. In other words, it's not really useful to think about a completely bare prior that depends on nothing. The probability of any hypothesis depends in your mind on some background experience you've had, and real dyed-in-the-wool Bayesians try to follow that by never writing down a bare prior, but always writing things as, for example, the probability of a hypothesis given capital I, and capital I is just supposed to be background information known to you about the hypotheses. It might just be that the hypotheses are equiprobable, that you don't really know anything else than that. That you have nothing to move you off of that symmetric hypothesis. But that would still fit this notation. Let's talk a little bit more about Bayes' law as a calculus of inference. And here's a famous example that instead of using Bayes' law asks what conclusion would we come to if we just use a piece of folk wisdom about inference. So this example is called Hempel's Paradox. And the folk wisdom is this, that when you witness a case of a hypothesis, it should add support to that hypothesis. Okay? So an example is the hypothesis that all crows are black is, in this folk wisdom, supported by each new observation of a black crow. You go through life and you see a crow and it's black, and then sometime later you see another crow and it's black, and by the time you've seen 1,000 crows, you say to yourself, I think that all crows are black. Sounds very reasonable. Now let's look at what Hempel pointed out about this. The statement, all crows are black, is exactly logically equivalent to the statement that all non-black things are non-crows. This is called the equivalence of a statement, and it's contrapositive. But just think about it for a minute. If you ever saw a non-black thing that was a crow, then that would disprove this statement. Okay? Whereas if all crows are black, you'll never see a non-black thing which is a crow. I think I've said that right. But anyway, all non-black things are non-crows is the same statement as all crows are black. But now let's look at the folk wisdom. The folk wisdom says that every time I see a non-black thing and it's a non-crow, then that is evidence in support of this hypothesis. In particular, the observation of a white shoe is such an observation. Therefore, Hempel pointed out, the observation of a white shoe is evidence that all crows are black. Do you believe that? Well, the resolution of this paradox was pointed out now quite a long time ago by a famous statistician, I.J. Good, in a paper with the amusing title, "The White Shoe is a Red Herring." And Good said to us, let's simplify this problem. Let's suppose that instead of all possible worlds of birds, there are really only two hypotheses that we have to work with. We might be in world 1, in which there are 1,000,000 birds, exactly 1,000,000 birds, and 100 of them are crows, all black. And all of these other birds are not crows. Doesn't matter whether they're black or not, but here I've drawn them as non-black. Now in the second world, we also have exactly 1 million birds. 200,000 of those birds are black crows, and 1.8 million of them are white crows. We observe one bird, and it is a black crow. And we want to ask the two questions. Which world do we live in? And are all crows black? Of course, we're not going to get definitive answers from observing one bird, but let's see from a Bayesian perspective what kind of inferences we can make from this observation of one bird at random as a black crow. So we're going to apply Bayes' theorem. We're going to save a little bit of calculation by not calculating Bayes' denominators. How can I do that? Well, if you write down Bayes' theorem twice, once for the probability of H1 given D, and once for the probability of H2 given D, and you divide those two probabilities, then on the Bayes' law side, you'll have the same Bayes' denominator, so it in both numerator and denominator here, so it divides out, and you just get the quotient of the Bayes numerators here. And that's called the Bayes odds ratio, and it's simply a computational convenience when you don't want to be bothered calculating denominators. So let's calculate the Bayes odds ratio, the ratio of probabilities that we're in world 1 versus that we're in world 2. Okay. So Bayes tells us that the numerator is the probability of seeing a black crow given that we're in world 1. So that's 100 out of a million, or 10 to the minus 4, times the probability that we're in world 1, the prior probability, and I'll just call that P of H1. I won't have to evaluate it. And then in the denominator, it's the probability of the data, the probability of seeing the black crow, given that we're in world 2. And in world 2, 1/10 of all the birds are black crows, so that's 0.1. Okay, so simply carrying through these prior probabilities without trying to evaluate them numerically, you see that this is a small number, 0.001, and therefore whatever our odds ratio was before, it's now 1,000 times less. That means that we should believe in world 1 1,000 times with 1/1000th of the probability that we did previously. So the observation strongly supports H2, that we're in world 2, and the existence of white crows. This is an example where the observation of a black crow supports the hypothesis that there exist white crows. We see that Hempel's folk wisdom is simply not true. What is true is that data supports the hypotheses in which the data, is more likely compared to other hypotheses in which it is less likely. And that's exactly the content of Bayes, that completely independent of what we take as the priors, this ratio says that if the data is more likely in H1 than it is in H2, then the data will support H1. And if the data is less likely in H1 than in H2, the data will support H2. What we also see in this example is that we have to have some kind of background information about the universe of hypotheses. Otherwise, data just has no meaning at all. The problem with the folk wisdom is it didn't lay out explicitly this requirement. It said, so you observe a black crow, so that means that all crows are black, or adds weight to the hypothesis that all crows are black. But it depends on what is the range of possible worlds that you might be in when you observe that black crow. And what Bayes, as a calculus of inference, does is it makes that dependence explicit. Congratulations. If you've followed the argument in the previous example, you're now a Bayesian. And what does that mean? That means that you understand that probabilities are modified by data, and that this makes them intrinsically subjective, in the sense that different observers have access to different amounts of data and different background information or background knowledge. And so in those situations, different observers will assess the probabilities of things differently. That's the sense in which Bayes probabilities are subjective. This picture is a picture that you get on Google Images if you look up the word subjective. I must say, it looks to me more like a picture of schizophrenic. And there's nothing schizophrenic about being a Bayesian, because Bayes, in principle, gives you a complete calculus of inference. Notice that the connection of probability to what you might have heard in the past, frequency of occurrence of repeated events, is now a very complicated thing. Because if we wanted to interpret your subjective probability as frequency of occurrence of repeated events, we'd have to repeat the exact state of your knowledge. We'd have to clone you into a parallel universe and give you all the same background information to be able to say what frequency of occurrence of events is about. So to a Bayesian, it's not a very useful concept to think of probability as being the frequency of occurrence of repeated events.